to the next part of the lesson shortly after. We had two numbers left. Remember, we were looking at impulse. We were looking at impulse and momentum, and we had defined impulse as the product of the force and the time for which the force acts on a particle or on a body. So if we may recall before we look at the actual questions, we said that impulse, which we can denote with letter I, is force times time. Let us remind ourselves, we said impulse is force times time, but we are aware that force is mass times acceleration. And we are aware also that acceleration is velocity minus final velocity minus initial velocity over time. These are three expressions. When we fit in the expression for force here, we get our first equation here. When we substitute in for force, we get our impulse as the mass times the acceleration times the time. And when we substitute in for acceleration, we get our impulse as mass into v minus u over t times t, which finally gives us that impulse is actually the change in momentum. And this one. So apart from impulse being the product of force and time, we were able to see that impulse can actually be the change in momentum, where m is the mass, v is the final velocity, and u is the initial velocity. We now focus on to the solution for the first number of the exercise. Definitely, as usual, I want to thank the students that continue to work through these numbers, starting with those that usually work through the numbers even before I reach home and send me a feedback. For those that worked through and you're not sure whether you got the correct answer, let us work through number one. We are given a mass. The mass of the bullet is 30 grams. We shall convert it into SI units, which will be 30 out of 1,000 kilograms. We can simplify this to get 3 out of 100 kg. We are given that it is fired into a wooden block at a speed, the initial speed of the bullet is 300 meters per second, and it is broad traced in that time. Broad traced means that the final velocity of this bullet is 0, and this happens in 0.03 seconds. And they want us to find the average resistance. They actually want us to find the force. They want us to find the force. The average resistance is going to be the force. So, if we use our expression that force is mass into the change in velocity, v minus u over t, we shall be able to actually get the resistance that we need here. And this resistance is going to be obtained by, of course, getting the force. We know the mass, so if we substitute in, we have 3 out of 100 times the change in velocity will be the net change. We can say 0 minus 300 over the time, 0.03 3. This is going to give us a value of 3 times 300 over 100 times 0.03. When we compute this, we shall get a value of negative 300. These two zeros will drive the decimal point out of here, giving us 900 out of 3. And this will give us the resistance as 300 newtons. The resistance, or what we have called the average resistance, will be 300 newtons. The average resistance will be 300 newtons. The negative value here can be ignored by taking the magnitude. Remember, force is a vector quantity, and therefore we can take a magnitude. Alternatively, we could feed in this as a magnitude, and we say it is 300 minus 0. So we are saying that the average resistance will be equal to 300 newtons. When we move to the second question, they have again given us mass. The particle has a mass. The mass is 0.5 kilogram. It is moving with a velocity of, this is the initial velocity, 6I minus 7J. They are saying when it is given an impulse, they have given us the impulse as 3I plus 11J. They want us to find the final velocity, V. To the students following this program, I want to advise you that it is always very important to identify what they have given you and identify what they want you to find. Identify what they have given in the question and what they want you to find. That will quickly lead you to identifying the right or appropriate formula to use. So we already know that impulse, just like we started the formula or the lesson, impulse is given by the change in momentum. We shall use the fact that impulse is equal to momentum change, or momentum before collision minus momentum after collision. And now that we want V, and we have the mass, we have the initial velocity, we have the impulse, we can say that our impulse, which is 3I plus 11J, should now be equal to 1/2. If I factor it out, the mass is 1/2, into the V, which we actually want, minus the U. The U is 6I minus 7J. Here, we need to put that bracket there, otherwise the computation will not be right. Since we want V, we can multiply by 1/2 both sides. Multiply by 2 both sides to eliminate the 1/2 here. These two will go with that 1/2. And we shall have our 6I plus 22J being actually equal to V minus, I'm opening this bracket here, so I'll stay with 6I, and this becomes a plus 7J. I will stay with the V which I want over here by carrying the whole of this and bringing it there. So my V finally will actually be 6I plus 6I. This 6I crosses to become a positive, it adds itself there, plus 22J. This 7I will cross to be taken away from the 22, meaning that our final velocity will be 12I plus 22 minus 7 will give us 15 plus 15J. The velocity which we want is actually this velocity here of 12I plus 15J. We shall get our velocity as 12I plus 15J. If this velocity had units over here, it is incumbent upon the candidate to put the units. If it has units of meters per second, you are expected to attach that unit there. So our velocity is obtained as that. And for those of you that tried out these two numbers, you can now confidently say that you got them right. You can confidently say that you got these numbers right. As usual, I will allow some time for those capturing the working to actually capture the working. Remember, there are three lead points: that impulse is force times time, but force is mass times acceleration, and acceleration is change in velocity over time. When we feed in acceleration here, we get another expression for impulse as change in momentum. So depending on the information they have given you in the question, you can actually find impulse by getting force times time directly. We looked at that. But you can also find impulse by using change in momentum, as we have seen in the second number over here. As we have seen in our second number over here, you can be able to find impulse. As the solution, you will allow me to clear off the question area as we wait to look at the next concept. I hope that you're now done with capturing that. I want us to look at the next part that we partly defined in our introductory lesson. We talked about momentum. Remember, the heading was momentum and impulse. And we talked about momentum. I want us to strongly move in and now focus on momentum. I told you that this is mathematics, and by the nature of the subject, we are not going to be asked questions to define, but it is important that we know what momentum is. We said momentum can be defined as the product of mass and velocity of a body. The product of mass and velocity of a body. And we said, in terms of the expression, you can say that momentum is actually equal to mass times velocity. Mass times velocity. In our discussion today, we are interested in finding out what I will call the law of conservation of momentum. The law of conservation of momentum. Now, momentum deals with bodies that are moving, and these bodies have a mass. And since these bodies have a mass, it implies that if they are moving, they have a velocity which actually will change. So, before we state this law, we are going to consider a body of mass. If this body has a mass m kilograms, we shall call it m1 kilograms, moving with a velocity. If we consider this body is moving with a velocity u1 meters per second, and this body eventually collides with another body, if it collides with another body of mass m2 kilograms, also initially moving with a velocity u2 meters per second. There are two types of collision here that we shall talk about. When these bodies collide, there is a possibility that they can move together. That is condition one, or possibility one. There is also a possibility that they can move separately. Now, if they move together, they move with a velocity that we call in science common velocity. If they separate after collision, they will move with different velocities. And these types of collision are different. Where they move with a common velocity, we say that the collision is inelastic. And where they move with different velocities and separately, we say that the collision is elastic. So we shall consider that this time round, they have an elastic collision. Body one is moving with velocity u1 and has a mass m1. It collides with body 2 of mass m2, which is moving with u2. And if after collision, the bodies move separately, if they move separately, with new velocities v1 and v2 respectively, then we can say that during collision there was a force that was involved that caused the change in this velocity, as we may be aware. Then we can be able to look at the expressions. They move separately with different velocities, v1 and v2. This would imply that if we look at these cases, we can look at a case now before collision. What is happening? We have This body 1, which I'm calling M1, it is moving with the velocity U1. We also have body B or 2 with a mass M2 moving with the velocity U2. That is before collision. We can call this part A. During collision, these bodies are expected to now have collided, so they are in contact. They are in contact. This, remember, is M1. It will receive an impulse that is associated with a force due to body 2. And similarly, M2 will receive an impulse associated with body with force M1. And after collision, we have said these bodies are going to move separately. If after collision they move separately with different velocities, then it implies that we are looking at M1 and M2. M1 now moves with the velocity, and by our definitions, you can tell that the symbols we are using are actually illustrating that now they attain the velocity that we can call final velocity. After collision, they have attained new velocities, and therefore they are moving with that. If the impact at collision takes a time t, if it takes a time t, we can therefore be able to derive different expressions. We can be able to derive different expressions. We can say before collision, the momentum can be got as M1, U1, and M2, U2. After collision, the momentum can be got. But we want to derive an expression for conservation of momentum. So using the formula that force is equal to MA, we shall say for the body of mass M1, since the velocity has changed from U1 to V1, the force acting on M1 is 2. Since we know that A is V minus U over T, it means the force F2 acting on M1 causes the change in velocity. It causes the change in velocity in the said time t, implying that therefore the force F2 will change the mass or the momentum of body with mass M1 to give us M1 into V1 minus U1 over the time t. And in a similar way, similarly, F1 acts on M2 and causes the change as well, causes velocity change. This implies that actually F1 will also be equal to the change in momentum of the second object or the second body within the same time interval t. By using Newton's laws of motion, we are able to prove the third law of motion specifically states that the forces F1 should be equal and opposite. So if F1 is equal to negative F2 or the other way around, does not matter. F2 can be equal to negative F1. It is the same. It implies that if we apply, I will use this one, my F1 is now M2 V2 minus U2 out of T should be equal to negative F2, which is negative M1 into V1 minus U1 over T. Definitely, the time T will cancel. And if we rearrange, we shall have M2 V2 minus M2 U2 being equal to negative M1 V1 plus M1 U1. This negative times the negative will give me a positive there. If I rearrange, I finally will be able to get the M1 U1 plus M2 U2 being equal to M1 V1 plus M2 V2. If you're following this lesson, I want to tell you that the expression we have gotten now confirms that actually there is what I would call you conservation. I will tell you is called conservation of momentum. I will shortly state that the law of conservation of momentum, which we are yet to state, but which is depicted by the expression we have just got, states that in a system of colliding bodies, the total momentum before collision is equal to the total momentum after collision. The word conservation means that you don't lose. The momentum that you have before collision is exactly equal to the momentum after collision. In a system of colliding bodies, momentum is always conserved. This expression is going to help us to work through a number of questions in the next few minutes. But as usually I tell you to take a picture. I will pause a little bit for you to be able to capture whatever is on the board in the interest of good stewardship. This concept is also very good for students that are offering physics, and it cuts across. It is good for the senior 3 students. It is good for the senior 5 students, those of you that are still at home. And of course, for the senior 6 students that are in different schools right now, those that have access to media and can watch this lesson, this information is good both for applied maths in physics. We shall conclude and shortly move into examples. We shall be concluding this derivation and move into examples. Take note that in mathematics, they will not ask you to prove. They will not ask you to prove this question or this formula or this derivation. They will simply ask you to apply it. It is important to note that, one, momentum is conserved in both types of collision. Momentum is conserved in both types of collision. I will say in both elastic and inelastic collisions. It is important to note that momentum is conserved in both elastic and inelastic collisions. And in a perfectly elastic collision, whose expression we have just derived, we can say that both momentum and kinetic energy are conserved. Both momentum and kinetic energy are conserved. Both momentum and kinetic energy are conserved. It is also important to note that momentum is actually a vector quantity. This information is very important for us to progress. Not also that initial momentum from the expression I've got is m1 times u1 plus m2 times u2. And final momentum is m1 v1 plus m2 v2 for a body that, or for bodies that move separately after. I can also say that B, for bodies that move together, after collision, we say that momentum before collision, the total momentum before collision, will be equal to the momentum, the sum of the masses times the common velocity. We say this V is the common velocity, where V is the common velocity. Questions can be set, and they are telling you to find the common velocity, and that expression, this expression here, will come in handy. Will come in handy for the candidates to be able to actually find the common velocity or any other relevant information the examiner may want. So we shall have our first example here on the use of the law of conservation of momentum. Very simple concept once the candidate gets to know what is given. Our question is over here. A particle has a mass of 2 kilograms. It's moving at a speed of 10 meters per second, collides with a stationary particle also of known mass. The mass of the particle is 7 kilograms. If the particles move together, after collision or after impact, with a speed of they are telling us they move together after impact with a common speed. They move with the same speed, but in opposite directions. They move with the same speed, but in opposite directions. They want us to find the loss in energy, the loss in kinetic energy. They are saying find the loss in kinetic energy after collision. After collision. Find the loss in kinetic energy after collision. I always advise students, whether you're in an exam, whether you're revising privately, it is important that you always read through the question the second time. It is important that you always read through the question the second time. I repeat, it is important that you always read through the question the second time. The question is over here, and since our time is first spent, we shall interpret it and be able to allow time for the candidates following this lesson to copy the solution after. We have two cases or two particles. The first one has a mass of 2 kilograms and it is moving with the velocity or the speed, which is the initial speed of 10 meters per second. The second particle has a mass of 7 kilograms, and they are saying it is at rest. Stationary means that it is not moving. Then they are saying the particles move together after impact. After impact, these particles move together. After impact, they move together after impact with the same speed but in opposite directions. So it means that after impact, if this is the 2 kilogram mass, it can move in this direction And if this is a 7 kilogram mass, they are saying they move together, it should be able to move because they're saying in opposite directions to move this side, but with the same speed. Since they want us to find the kinetic energy change, we shall be able to find the kinetic energy before collision. Before collision, kinetic energy will be, we are all aware that kinetic energy is given by a half times mass times velocity squared. So it will be a half times mass 1, which is 2, times the velocity there squared, plus a half times mass 2, which is 7, times the velocity squared. And when we compute this, this will give us 100 joules. Because this 2 will cancel, and this is 0. After collision, the kinetic energy will be a half times the mass times u squared plus a half times the mass of the second one times u squared. This is going to cancel, and this will give us 3.5 u squared plus u squared, which will give us 4.5 u squared joules. That is the kinetic energy. But since they are telling us they move with the same speed, by conservation of momentum, we keep these values there. By conservation of momentum, momentum before collision will be 2 times 10 plus 7 times 0, and should be equal to 2 times minus u plus 7 times u. Because this is moving in a negative direction, it is negative. So our 20 will be equivalent to 5 minus 2, 7 minus 2, which will give us 5u, implying that the u is actually going to be 4 meters per second. That common velocity which we need here is going to be 4 meters per second. After getting that common velocity, we can get the kinetic energy after collision, which is given by that expression there. We can get our kinetic energy after collision. This implies that Ke after collision is, this was u squared plus 3.5, which is 4.5. So it is 4.5 times 16. When we compute this, it should be able to give us 64 plus 4 times 60 times 16 is 64, and we add on 8. That will give us 72 joules. That will give us 72 joules. So the kinetic energy before is 100. The kinetic energy after is 72. And therefore, we can get the change or the loss in kinetic energy. The loss in kinetic energy can now be obtained from there. We can get our loss in kinetic energy. Would be equal to the kinetic energy before minus the kinetic energy after. And this is going to be 100 minus 72, which would definitely give us 28 joules. So our loss in KE is equal to 28 joules, and that is what this question required us to find. That is what this question required us to find. You must find the kinetic energy before, kinetic energy after, but since we need the initial velocity, the velocity after impact, which I called u, we need to find its value. And then feed it in, get the kinetic energy after, subtract the two to get the loss in kinetic energy. Usually we say that the kinetic energy after is usually smaller than the kinetic energy before, because energy is lost in form of heat and sound during collision. Energy is usually lost in form of heat and sound during collision. The reason why the kinetic energy before is always less than the kinetic energy after. I'll put a few questions here that you can try out. I'll put a few questions here that you can try out in the interval between now and when we meet next, as this lesson comes to the end. A car of mass 1,000 kilograms. Traveling at uniform velocity of 20 meters per second collides perfectly. Collides perfectly, inelastically, with a stationary car. When they say stationary, it means that car is not moving, it's at rest. Of mass 1,500 kilograms. They want us to calculate the loss in kinetic energy as a result of collision. Perfectly, inelastically is the key word here you need to find out. And I want to say that is one of the questions. The other question would require you to use differentiation. We shall discuss this, but I can summarize it and say a particle of mass 0.4 kilograms has a position vector, a position r being equal to t squared plus 4t into I plus 3t minus t cubed into j, where t is time and r is the position. They want you to find the speed. Find the speed find the speed of the particle at t is equal to 3 seconds. Find the speed of the particle at t is equal to 3. This is a position, and to find speed, speed is defined as the rate of change of distance with the time. Distance divided by the time. The speed would require you to differentiate this expression and then substitute in the value of time. As we wind up our lesson, I want to remind you that, of course, when we meet next, we shall be starting from there. Inelastic collision is where bodies move together after collision. And we have said elastic collision is where they move separately with different velocities after collision. Inelastic, they move with a common velocity. Elastic, they move separately. And we talked about that momentum is conserved in both types of collision, but kinetic energy is only conserved in a perfectly elastic collision. I want to remind you to continue reading. I want to wish you a nice weekend. And of course, before I get out of the studio, I want to encourage you to make sure you have captured this thing. Take a picture of the question or the exercise questions, work through them. As usual, those that are able to send the answers, please send them. Those that are not, we shall be able to look at this number the next time I appear here. Enjoy your weekend. Keep following the SOPs. Remember, COVID is there. It is real, and we all want to survive it. God bless you. Gachali Mabaga.
Bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'Ebombo Kalule n'eye Kabalagala tobona bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuuka ku siniya ey'omukaaga, nga tusomesa abaana okuviira ddala ku mutendero gwa kindergarten okutuuka ku kibiina eky'omusanvu. Tulina abasomesa abakugu mu kubangula abaana n'okubateekateeka. Ebibiina abaana mwe basomera eby'omulembe omuli buli kimu ekikwata ku ebyo bye basoma, ebisuula ebyazimbibwa obulungi, ebigazi ate nga biyonjo. Okumanya ebisingawo tukubire ku nnamba z'essimu ez'owammanga.
For the first time in Uganda, Africell introduces the first ever 4G Vita K242 Feature Plus phone at only 120,000 shillings. Watch videos on YouTube, share pictures, chat with friends on Facebook, and enjoy access to the internet with 1.5 GB of data and 850 Africell minutes every month for 6 months. Google Assistant, up to 8 GB memory card, dual SIM, selfie and rear camera, strong battery, and FM radio. Hurry and get yours! Because this is 100% value for your money. The 4G Vita K242 is now available at all Africell service centers across the country. Terms and conditions apply. Africell is regulated by the Uganda Communications Commission.
Okwerinda ekirwadde kya coronavirus ekiyitibwa COVID-19. Tufaayo nnyo